Kepler's third law. So I have been working on demonstrating Kepler's laws. I've already done the first and second law. I'm not going to show that they're true. I'm going to show that they agree with actual calculations. I'm not going to derive Kepler's third law, just to be clear. But this is more fun anyway. So let me give a quick review of the first and second law. Then I'll talk about the third law, and then I'll talk about what we're going to do to calculate the trajectory of a planet around the star and verify the third law. So the first law, Kepler's first law, and just to be clear, Kepler did not use physics for this. He just looked at data and said, okay, these things apply to the orbits of planets around a star. So the first law says that if you have a planet right there and a star, then the planet will orbit the star. And the shape of that path is an ellipse with the sun at one of the foci. And then there is another foci there. And so this actually is important. We do have, for an ellipse, we have the two parameters b and a. B is the distance from the center of the ellipse to the furthest away point in the y direction, if you want to call that the y. And then a is the same thing in the x direction. So this is in this shape, if the foci are on the x-axis, b will be in the y direction, and that will be the semi-major axis. A will be in the x direction, and that will be the major axis. Then we have Kepler's second law. We're in second law. Kepler's second law says that if you look at the motion of a planet orbiting the star, as it gets closer to the star, it speeds up, and then it gets slower as it's further away. And one way to quantify this is the equal areas equal time rule. So this says if you start with the planet right here and you let it go for a month, then it will it'll cut out this sector, and you can find the area of that. Over here, if you do, again, 1 month from here to there, it will sweep out a different area, a different shape, but these two areas will be the same. Okay, and so this is going to be bigger because it's going faster. Finally, we get to Kepler's third law. Kepler's third law says that if you measure the period, the time it takes to go all the way around, that is related to the semi-major axis. And so we have this. The period squared is proportional to the semi-major axis cubed. And so that's what I want to show. In fact, this is pretty easy to show using physics if it's a circular orbit. It's possible to do it for elliptical. Most books just show this for circular and say, see, it works. Because for a circular orbit, A and B are the same. But what I am going to do is to model the motion of a planet going around the star, and then measure the period and measure B, and then change those and show that this relationship is true. So I'm going to make a plot of period squared versus B for different orbits. It's going to be fun. I'm looking forward to it. Okay, so here's what we're going to do. We're going to start off with a planet at a star at the origin and some planet over here, a vector location R. It has a momentum p, has a mass lowercase m. The mass of the star is m. I can calculate the gravitational force, the vector gravitational force on this mass. It's going to be negative g, mass of the star, mass of the planet, times r hat, which is a unit vector in the r direction, divided by the magnitude of this distance squared. Now, if I break this into small time steps, and I use a small time step, and so small is relative, right? But if I use a small time step, I can assume that the gravitational force, this vector force, is constant. And if the force is constant, I can use the momentum principle. The net force is the change in momentum with respect to time. And I can find the momentum at the end of the time interval if I know the momentum at the beginning, because it's just final minus initial. So I can write that down here. P2 is the momentum at the end of that small time interval. P1 is the beginning. So the initial momentum plus F delta t gives me my new momentum. Now I can assume that the momentum is constant, which it's not, but I can assume that. And then I can use the same thing to find the velocity, P over m, and use the same thing for velocity change in position over time to find the new position. So the new position is the old position plus the velocity, at the end of the time interval, that's why it's P2, times delta t. And then I can update time and then do it again. So I have a whole bunch of calculations to do, but who cares? I'm going to make Python do it. Now, one more thing, just to make things simple, because I don't really care about the actual numbers. I'm just going to make all my constants 1 to begin with. You can change that. You could put in the real gravitational constant g. You could put in the mass of the sun, the mass of the Earth, the radius, orbital radius, and the velocity, but I just don't really care. Okay, it's still going to work. As long as I have a 1 over r squared force, which I do, this should work. Okay, let's jump over to Python and get started. Okay, so I'm using Web VPython. It's called GlowScript Python VPython also. And the nice thing about this is it has a bunch of stuff built in. It has stuff built in for graphing. It has stuff built in for handling of vectors. It has stuff built in to 3D model stuff. So I can actually draw the sun and the planet orbiting. I'm not going to do that this time. Okay, I've done it in the past too. I'm just going to do the calculations. So I've already got things started. I already have my graph set up. That's why I need to make a graph, and that's the function I'm going to plot. And there's all my variables. Oh, let's put that at 1. I'll change it later. So the other thing I need to do is to put my initial condition. So my initial position, I'm going to actually call this our start, and it's going to be a vector r1, 0, 0. I'm going to start on the x-axis with a velocity on the y-axis. So I know that's going to force the foci to be on the x-axis. And then I'm going to say, and then I'm going to say r is equal to r start. Right, so they're going to be the same. So r start I'm not going to change. I'm going to keep that starting position the same. But r is going to be my changing variable. I need my momentum vector, p. It's going to be mass times vector, not that, 0, v1, 0. Right, so it's going to be in the positive y direction. I need time, t equals 0. My time step, let's put 0.01. Oh, up here, this dot equals true. That's just going to make sure it leaves a dot when it draws the curves, just so I can see where it's drawing. Okay, let's do something like this. While t is less than 5, I'm just going to do it until t is 5. And I'm not saying that's 5 seconds. I'm saying it's 5. Okay, so I didn't put my units in here, so it's not really wrong. I'm just using some time interval. So the first thing I'm going to do is to calculate the gravitational force. Oh, I'm going to do this, rate 1000. Let's put that in there. That's going to make it draw the graph in real time. And I'm making a graph because I'm going to be using functions later, so I don't have to make a graph. But this is going to be a trajectory graph. So the first thing I'm going to do is to calculate the gravitational force. Negative g times m times norm r. Norm is a built-in function in GlowScript that is the unit vector in the direction of r, so it's r hat. And then mag is a built-in function that returns the magnitude of a vector, but I need to square that. In Python, square is star, and then whatever, 2. Now I'm going to update the momentum. P equals p plus f times dt. That's all. Update the position. R equals r plus p times dt over m. Update time. Now I'm going to plot it, actually. So let's plot. F1 dot plot. I want to plot x versus y. I want a trajectory. So I'm going to say r dot x is the x component of the vector r. R dot y is the y component. Now I'm going to update time. T equals t plus dt. And let's run this thing. And I'm going to give you the code. Okay, so that's looking pretty nice. So notice that this is not a 1-to-1 scale. I think it's actually a circle, because this goes from -1 to 1, and this is, see, that's -1 to 1. So it looks like a circle. But it didn't make it all the way around, so we can fix that. I could just go up here, and I'm going to run it for a little bit longer. Let's say 7 seconds. Let's see if that's enough. Not that it really matters. It's going kind of slow. Okay, so that made it some and more. Now, but what I want to do, I need 2 things from this, right? Number 1, I need this time. I need to know what time it gets back over here. So what I'm going to do is to use that start variable, r start. and I'm going to calculate the difference between the position of the planet and the R start. And when that value is small enough, I'm going to stop it. So it's going to start over here, and when it gets back over here and it's really close, I'm going to say stop. Now, I do have to be careful, right? Because it's going to start off right there. So it's going to start and just stop. It's like it's already there. So I'm going to put in a double check. I want to say if t is greater than 1, I just pick one value. And it's very close, then I'll stop it. And that should give me the period. So let's add that in there. So to do that, the first thing I'm going to do is make a variable called orbit equals true. So I don't want to do it for a time. I want to do it until orbit is no longer true. So I'm going to say while orbit true. So while orbit, that's it. If orbit's true, it keeps doing it. I don't want to do this anymore. Now let's calculate r diff. So I'll put it right here. R diff equals r minus r start. Then I'm going to say if the magnitude of r diff is less than 0.001 and t is greater than 1, then orbit equals false. Right, so both of those things have to be true. If both those things are true, I'm going to change that Boolean variable orbit to false, and then when it gets back up to the top of the loop, it's going to stop. Now, down here, let's put this. Let's say t equals t, right? So I'm using t as my period, and it's whenever it stops, that's what the time is. So then I'm going to print that. Print t equals t. I'm going to leave off the units because I don't want to put it in there. So run that. So it did it, and it looks like it stopped at the right spot. And then I get a period of 6.283. Now let's just change it. So one of the things I can do, if I shoot it with a smaller velocity, then it's going to come in closer to the vertical axis, and it should take less time. It actually should take less time to go around. So let's do that. That's one way to. I just want to change b and t. I want to change those two things. So if I go up here, let's just put the initial velocity at 0.7 and run it. And let's see if we get a different time. Again, it looks different. That's fine. Doesn't really matter. But I do get a different time. Okay. Okay, so I've got that. Now the next thing I need to do is to find A and B. So A is going to be the distance from here, the center, which is not the origin, right? That's not the origin. The origin is actually over here where the star is. I can put a dot there if you want to, but it doesn't really matter. So one thing I can do is I know the starting position over here is at one end. If I find this position over there, then I'll have the two endpoints. And then if I just take the difference between those and divide by 2, I'll get A. I can do the same thing up here for the point up here and the point down there. So I just need to find those 2 points. Okay. So let's do this. This is a little trick. So I'm going to go down here. I'm going to say A1 equals R start. A2 equals R start. I'm setting these as vectors. B1 equals R start. B2 equals R start. So I have 4 points, and they all start at the same location. As I move around, when I get to that top, what's true about the top up there? Well, the top, I know that the x value is, the y value is positive, and it goes from going, that top point, it's going up, and then it's going back down. So the y velocity is going to be very close to 0. So I want to look at when that y velocity is very close to 0 and y is greater than 0. So in the loop, I can put down here, let's put it right here, if r dot y is greater than 0, and I want the absolute value of the momentum, because I don't have the velocity at the momentum, but I'm just going to use the norm of the momentum, which is the unit vector, because I don't really care about the actual values. So I'm going to say, and the absolute value of the norm of p dot y is less than 0.01. If that's true, then b1, which is the top part, equals r. because I've been moving around, right? If that's where I'm at, then that's my B1. Now to find B2, it looks like this. If r dot y is less than 0 and ABS norm P dot y is less than 0.01, that's going to be B2, right? 'Cause the difference is it's a negative y value. Now I need to find A2. So I'm going to say if r dot x is less than 0, because it's on the negative side, and ABS norm P dot x is less than 0.01, then A2 equals R. So now I'm not going to move A1. It's already at the right location. Okay, so now after the loop, I can find, let's find A. A is going to be the magnitude of A1 minus A2 divided by 2, right? Because once I know that distance, actually, let's do this. Let's just not do the magnitude. Let's do A1 dot x minus A2 dot x. I don't really care about the y values. And divide that by 2, that's going to be my A value. And then I can do the same thing. B equals B. Oh, this should be B2. A1. This should be A2 minus A1. Or it'll give me a negative number, which isn't that bad. But B2 dot y minus B1 dot y divided by 2. And let's print those. Print A equals A. Print B equals B. Run it. Okay, so we have some values. We have t. Oh, it did give me negative. I got that backwards. Final minus initial. I want to fix that. That'd bother me. Okay, so this would be backwards. A1. I don't know why. A1 minus A2. 2. 1. Okay. Okay. So A is 0.66. So let's see if that's right. Let's just check. So here is the center. Actually, that one's going to be harder to check. Let's check the B, because I know the B. The B is 0.56. So I know this is the location, and I'm pointing at the screen. It doesn't really help. And it's down there, so I know this distance. If I mouse over right there, I get 0.569. So it looks pretty close enough. Okay, so that is giving me the B value. It seems to be working. Now, what do we do? I could just manually change this, get B, get T, collect a bunch of data, but I'm not going to do that. I'm going to make a function, and then I can change the parameters of this function, and everything's going to be great. So I want an orbital function, and I'm not going to make a graph in the function anymore. I'm going to let the thing go around. I'm going to give it initial conditions. I'm going to give it an initial position and initial velocity on the x-axis, moving in the y direction. And then I want the function to return the period, A, and B. I don't actually need A, but I'm going to do it anyway. So if you're not familiar with functions in Python, I do have a function tutorial in Python. And I'll try to remember to put it down below, but I often forget. So let's do this. Let's say up here, I'm going to say def Kepler. I'm going to call my function, which is pretty stupid. Let's call it orbital. That's pretty stupid too. Now, when we define a function in Python, we need to say what variables we're going to give it. In this case, the only ones I'm going to give it are R1 and V1. Everything else I'm going to do. I'm not going to change the mass. I'm not going to change the mass of the star. I'm not going to change those things. You could. I'm not going to. So then I put a colon. Now, everything in here, right here, I don't need these, right? I'm going to pass those values to my function. So I don't want to have those values. I don't want to assign them anything. I'll assign them later. Now, all of this stuff, I want to be part of the function. All of that stuff. I don't want to have this plot in there because I don't want to plot. Okay. So I'm going to take all of this, all of that. Now I'm going to get rid of the print stuff. And I'm going to indent it. And that's pretty nice because now it's indented as part of the loop. Let's get rid of these print statements because I don't want you printing things out. I don't want to print that out. I don't want to print that out. Okay. Now, I need to do this. Return some values. I'm going to return the values t, a, and b. And so once this runs through, it will give me those three values. So let's do this. I'm just going to do this in the simplest way. I'm going to say print. I'm just going to print it out. Orbital, the function. And I need to, if I go up here, I gave it R1 and V1. So let's just say the last time I did this, I had R1 was 1 and V1 was 0.7. And so it's going to print T, A, and B for that, which we just did, so it should work. It should give us the same thing. So that looks like it. There's my T. It's printed as a list. There's my A, and there's my B. It worked. Okay. Now we're ready to do some stuff. Okay. So let's do this. What we're going to do is to make a graph of t squared versus b cubed for a bunch of different values. So what I'm going to do, I'm just going to change v. I think I can just change v. So let's say v0 equals 0.3. I think that will work. And r0 equals 1. Now up here for my graph, we need to change my graph. I'm not going to graph x versus y. I'm going to graph b cubed versus t squared. Now, and I'm going to put this to 200 because I want to make it look like a normal graph. And I don't need dot. But I'm going to leave that thing right there. Okay. So what am I expecting? If those two are proportional and I plot t squared versus b cubed, then it should be a straight line. So I should get a straight line. Okay, down here, that's my initial velocity. How much am I going to change the velocity to, and how far am I going to go? Let's change this to, we don't have to be crazy. So let's say dv equals 0.05. And then I'm going to say while v0, I'm not sure why I'm calling it that, while v0 is less than, I want to go up to 1.5. Let's just try that. So the first thing I'm going to do is to calculate T, A, and B. So I can say this. I think I can say this. I'm trying to think actually. Let's test something real quick. Can I do this? TT, would it be? I think it's like this. TT, AT, BT equals orbital 1.7. Print TT. I think that's how you can do it. I forgot. Let's just run this. Okay, so it did. Let's see. And then if I print AT, and I'm calling it AT, so to not confuse with the other one, that should just print the T. Because the thing I'm returning, yeah, okay, that's working. So the thing is, I'm returning three values, and I want to use those three values. So let's go over here. I don't want to do this. Copy that out. Okay, so number one, I'm going to say TT, AT, BT, equals orbital, my R values is going to be R0, my V value is going to be V0, which is going to change. And then I'm going to plot, I'm going to make a plot, right? F1.plot on the x-axis, I said I was going to plot what? B cubed. So I'm going to say plot BT cubed versus TT squared. Now I'm going to increase the value of V. V0 equals V0 plus dV. And it should work. That should be it. I haven't saved this in a while. Let's save this because, disaster could happen. Okay, I'm kind of scared because that looks a little too simple, but let's just try this. Oh, something terribly awry. I have a feeling that what I did was to make a loop that never finished. Yeah, that must be what happened. Okay, let's see if I can just refresh that. It locked up. Okay. Oh, there it is. Okay, let's go down here. And let's say V0 is 0.7. I know it worked at that. And V is 1. I know it worked at those values. I tested them. Okay, so, and then I'll put this at 0.1. That should work. There. Okay. It's not a very big plot. I'm afraid to do... No, wait. Okay, that's right. It's plotting. I think this is okay. Straight line. Okay, now... Oh, undefined. What is it printing? Oh, print AT. That's not defined. Okay, so I think it is working. Let's go a little bit lower. See if we can go a little bit lower. If you want to, you could also change the property B. In fact, let's just go for gold here. Let's say now I'm going to say V0 equals 0.7 while R0 is less than 2. Then I'm going to do the same thing. I'm going to just add more to the graph. Oh, that's backspace. And now I'm going to increase my value of R, so I do need a dr. So say dr equals 0.2. R equals R plus dr. Now, it does take a little bit of time to run that loop, right? So there is a lot of computation going on here, so it won't run this instantly. But I think this should be okay. Run it. If it doesn't, I already have... Okay, so here it did come back on itself, and it gave a little bit different value, which is totally fine. Okay, but it's still, I think I am indeed showing that Kepler's third law is true. The orbital period squared is proportional to the semi-major axis cubed. And there you go. I will give you the code down below. I did say that I would give you a tutorial on functions if you want that. I will put a link to the other Kepler's law videos, and hopefully you find that interesting. I'll talk to you later.